Hosting provided by Host Tornado. They offer website hosting packages, dedicated servers, and VPS solutions. Host.t.net. Programming Throwdown, episode 26, Image Processing. Take it away, Patrick.
All right. I never know who's going to open the show. Then Jason just starts talking. We record that part like 10 times.
We both breathe in, we go,
and then whoever says it first.
Yeah.
Oh, see, I beat you. So first I want to talk about a new website. So actually, this is much belated, and I owe much apologies. My brother was nice enough to buy us programmingthrowdown.com for Christmas.
Pretty awesome.
And he actually built a little website there. So you guys can check that out, programmingthrowdown.com.
Yep.
That's spelled. No, I'm not going to spell it. It's too long. Google it. Programmingthrowdown.com, and so that's going to be our new website. We're gonna start, talking about that instead of our blogspot, programmingthrowdown.blogspot.com. That's too long.
Yeah, we removed Blogspot. We vivisected it.
Okay. We saved you a bunch of typing. Congratulations. So, anyways, you guys can check that out, and hopefully that'll be good for us. So, on to the news.
Yeah.
So we're recording this. The big news has been Sim City.
Oh my gosh, what a fail, man. So I've heard various things.
But I've heard people saying like it's addictive. Like, oh, you shouldn't play this because you'll lose like hours and hours and days of your lives.
Yeah, waiting for the server to allow you in.
I think they mean it's that good.
But yeah, what I've heard has been that basically, so there's two issues. There's a technical issue, which is that the servers have a very fixed number of people that they're allowing in, and so a lot of people just can't play the game after they bought it, which is kind of sad. Another issue is that they are doing microtransactions. So you kind of build your city up, your people are pretty happy, and all of a sudden Joe Brown wants to get from his residential district over into the city, and he needs a commuter train. What? Oh, that's going to be $2 of real money, right? So they've started this microtransactions, and it's just like League of Legends. You end up having to pay $500 if you want all the content or something.
Wow, okay.
League of Legends is pretty ridiculous.
So the fundamental issue here, to describe it, is that they decided, the makers of SimCity decided that they wanted this to be an online game.
Right.
So even though a large portion of SimCity has always been kind of focused on single player, and even this game largely is kind of a single player game, but you have interactions with other people's cities online, and then they're saying that they do a lot of the processing online. Like, it wouldn't be possible. People are like, oh, just make an offline version. Like, this online version's terrible. And they're saying, oh, but an online version is necessary because of the amount of modeling we want to do. Is we want to handle a lot of these things on our servers.
Oh,
well, that's great in a way.
City in the cloud.
But maybe that's not possible, right? If it wasn't ready and they didn't kind of expect it. But it's also hard because at launch, week, month, or whatever, everybody is going to be on at the same time. After that, people aren't going to be playing it as much. There's going to be people drop off, and so it goes way down. It's like when launching a product, this is like a common issue aside from the problems we can talk about SimCity. But when you launch, you have to balance this. You want to scale up if you're going to have a really, really big launch. Having a lot of servers, that's really expensive, and then you may not need them after that.
Right.
And so this balance of what is the, if you design for what peak capacity you can handle, you can't just make that infinite or you'll spend infinite money.
Yeah, exactly.
So
or even, you should make it elastic, right? So they should have jumped on some Amazon Web Services or something like that where they could, start off with a ton of servers, and as people dropped off, they could,
It probably is on Amazon. Well, I saw an article report kind of said it was connecting to Amazon servers.
Oh, really? Okay.
Yeah, so they'd already be doing that.
Apparently not well.
But yeah, it's do you think the world is ready? I don't think this is going to be isolated, right? I think this is the wave of the future games, which are requiring online, not just for DRM, which is a big thing. We've talked about that in the past, what happens when the DRM server's down or not working or whatever. But those are pretty relatively easy to alleviate most of the problems with, aside from the fundamental issue of DRM.
Right.
Eventually you could release a patch which disables the DRM if the server goes away. Whether or not they'll do that is a question. Right. But in general, you can make it that, it only has to check the DRM every month or something, right? Okay, fine. But this we're going to do a pair processing, a lot of the processing is happening in the cloud and you have a thin client in your house. This is the dream of 15, 20 years ago, right?
Yeah.
Like, everybody's going to have thin clients. We're all going to be connected to like massive machines in the back end. And
there was a thing where you'd play a PlayStation game over the internet without having a PlayStation.
So there's like OnLive, which does that.
That's right.
But that's not just PlayStation games, but yeah.
Yeah,
so I mean, this is like becoming more and more of the future, right? Or you can look at even some of the products coming out, like Google with their Chromebook thing, right? Like mostly Chromebook is a thin client. It doesn't do much except for run Chrome.
Yeah.
And then it depends on all the Google services in the cloud. So I feel like this is the old is new again.
I wonder if they'll make a Minecraft kind of like this, where everyone's playing in one huge world.
Oh, that'd
be pretty awesome.
Griefing would be a problem.
Oh, yeah. I just go in and just flood your house every day.
But yeah, that would be interesting, right? But you would need a server to do that, right? Like you would have to have like a legitimate, like very scalable big server.
Right. Yeah, totally.
That's interesting. We'll see.
That'd be pretty awesome.
Internet connections aren't that reliable yet in general. And then you have overloading, right? So I'm not sure we're ready for this.
Yeah, this might be a little too forward thinking. So my news of the day is news that shows Angular Strap. And so Angular Strap is a wrapper that somebody wrote, or a set of libraries that gives you bootstrap functionality in AngularJS. And I'll explain all of this.
Okay, good.
Bootstrap is a set of JavaScript libraries written by Twitter for Twitter, but they open sourced it so anyone can use it. And it handles a lot of things like modal dialogues. So, if you're in the browser, if you're writing some code for the browser and somebody, clicks on login, and you want to give them sort of like what feels like a new login window that they can't get out of when they put in, their username, password, and stuff like that. That's called a modal, M-O-D-A-L dialogue. And, Angular Bootstrap has a way of just doing this. Like you just say modal and then pass it some, text and things like that, and it creates one for you. So Twitter has a lot of these libraries that do all sorts of really cool things. And then let's talk about AngularJS. AngularJS is what's called a reactive programming library. So it's pretty cool. You make these declarative statements like, this section of the website will have the person's name. It's kind of like Prolog. I think we talked about Prolog in an earlier show. But you make a lot of these declarative statements, and then as you change variables, AngularJS sort of just does the right thing to make those declarative statements still true. So for example, if you say, take the person's username and put it here on the website, and the person not logged in, they have no name, it'll just put empty string, right? But then as soon as Patrick logs in, it's going to put Patrick there. Like you don't have to write any code saying, oh, Patrick's logged in, let's fill in the name. It just does it, right? So Angular Strap is all of the Twitter cool, awesome UI Bootstrap library, but written in AngularJS. So you can get the best of both worlds. And it's pretty freaking awesome. I have a link. You guys should definitely check it out if you want to do anything on the browser.
So have you used this yet?
I have actually used both of these. I haven't used Angular Strap, but I've used AngularJS, and I've actually used Bootstrap with AngularJS where I had to do the glue part myself.
Did you write this?
No, I did not write Angular Strap. Well, technically I wrote 1% of it, but they don't know that, and they rewrote it.
But you should have open sourced your 1%.
Yeah, it's true. They are the 99%. They have they've done this work for you, so you don't have to reinvent the wheel as I did, and it's definitely worth.
So be better than Jason and download this.
Yeah, check this out. Do yourself a favor and do me a favor, and check out Angular Strap.
All right. Well, time for Tool of the Show. You're up first.
All right, my tool of the show is I've been doing a lot of reading lately. Ever since we started Book of the Show, actually, I've been doing a lot more reading, and it's
I thought you were going to say since kindergarten.
Yeah, since we did Book of the Show and Tell, anyways. So I'm doing a lot of reading lately, both to have good books to share with you guys, and also just because it's kind of fun. So to do this reading, I've used Moonreader Pro, which is a pretty awesome Android app. I'll tell you guys about it. It synchronizes what page you're on with so if people are familiar with Google Reader, which where you can download books from the Google Store, and then you get the book on the tablet and the phone, and it keeps it in sync. So
is it Kindle Reader does this?
Oh, really? So if you read on the desktop, it'll keep your page.
Yeah, so it
good.
synchronizes what page you're on across your devices.
Yeah. So this does that, but for arbitrary PDFs, EPUBs, like any file format you want. So it's pretty amazing. Also, a really cool feature I like that the Adobe Reader doesn't have is it'll let you invert the colors. So I really don't like black text on a white background when the device is lit. Like on a Kindle it makes sense, but for a device that has an LCD panel, it really makes sense to have white text on black.
I don't think I've ever tried this.
Oh man, you should totally try. So they have a free version, which is Moonreader, not Pro, Moonreader free. Try this out, invert the colors, read white text on black background. I guarantee you'll love it. And then this app was only, when I bought it, it was only I think $2.
Do they have this on iOS?
I don't know. We can check.
Okay, yeah,
but basically, it uses Dropbox, so you need a Dropbox account, and it actually synchronizes your books and what page you're on using Dropbox. So I'm assuming
it doesn't
everyone
look like
has.
it's on. A brief search doesn't revel that it looks like it's on iOS.
Bummer. But if you have an Android device, definitely get Moonreader Pro. Best $2 you've ever spent. So.
Best. Wow, that's lofty statements.
I know. That pack of gum has nothing.
What about when you were,
Pro.
so dying of thirst in the desert, and that guy came by and sold you a bottle of water?
He charged me $3.
Oh, okay.
I know. It was brutal. But that was the best 2/3 of $3 ever spent.
Okay,
right.
I'm sorry, that was terrible.
So,
all right, so yours is
your
Android.
show?
Mine will be iOS, but mine's not a utility.
You're the yin to my yang.
I use the tool very loosely in this. Like, it doesn't have to actually be. So this is Space Team. This is a game.
Okay.
This is not a single player game. It's a multiplayer game, but it's local. I can't really show you because you don't have it, or else we could play it. But then people would be like, "What's going on?" So what this is it simulates you and the other people in your room. So you are together. You need to be together, and you're on the same Wi-Fi. Okay. And so it does a Wi-Fi link between your devices or whatever, and it simulates that you're all flying a spaceship.
Oh.
But your spaceship is having problems. Lots of problems. So that's kind of the theme, right? But in reality, what it is on your device, it gives you kind of a control panel with various different knobs or sliders or switches or push buttons or meters or whatever. And they're named very crazy things, right? So like the discombobulator, switch, the amazingness slider, named literally like this, right? And every person's device has different control pieces.
Okay.
So nobody's is the same. And then across the top of everybody's screen comes a different thing that needs to be done to continue flying the ship. But it may or may not be on your screen. So mine might say, move the pretty meter to 6. Well, I don't have pretty meter, so I have to shout, somebody move the pretty meter to 6.
Oh, but they don't know that they have to move.
They don't know because theirs says something else.
Oh.
And so I'm like, move the pretty meter to 6. Move the pretty meter. And you're saying something at the same time. You're saying, move the moon disk to 7. Move the moon disk to 7. Or sometimes it's words like, turn the space heater to cold. Or something like it could be anything, right? And so you're all shouting different things.
That's so good.
And then sometimes you'll realize you're shouting something that's actually you need to do. You'll hear somebody else, and you have to acknowledge it so the person can stop. But you kind of know because it'll go away. Because that's like a little timer. So the longer you take, if you take too long, your spaceship kind of has problems, right? Yeah. So then eventually stuff begins to go wrong. So the levels get harder. So if you keep going, it'll stop being words and being symbols. So instead of it'll just be this weird triangle with a circle around it symbol. Push that button.
Move that.
Yeah, it gets harder, right? But then also if you do bad, your panels will break. So green ooze might start coming down over the things and it's hard to see, or they might start dangling down from their screws and swinging back and forth, and you need to kind of pin them back in or try to tap them as they're swinging. So
that's so
it's
good.
really crazy and fun, and you typically die really quickly. But if you want to have a blast, I recommend this for people who are not in an area which needs to be quiet, and everybody's kind of goofy and in the same mood. But as a party game, this is a lot of fun.
Yeah, that's amazing. I'll have to check that out.
I forgot about that, but I had played that over Christmas with my family, and that was a lot of fun. So, but everybody else was like, "What are you guys doing?" And the more people, it actually gets kind of harder because then it's but it's funnier. Because people are screaming. Anyways, and I think it's free, so that's really good.
Oh wow!
And then I think you can buy they have additional features and missions and that kind of stuff or whatever. But I mean, for me, it was just kind of a good couple times to play it.
Yeah, it sounds amazing. I'm gonna have to check this out. So it's not for Android. I just looked it up, unfortunately, but maybe there'll be a maybe someone in the audience can look for a Moonreader Pro for iOS variant and a Space Team for Android, and we can be complete.
There we go. All right.
So it's time
for Book of the Show.
So my book of the show is Do Androids Dream of Electric Sheep?
I don't know, did
I? Spoiler alert. No, I'm just kidding. I won't tell you. But it's by Philip K. Dick, and it was pretty good. It's about sort of this futuristic world where they can make androids so real that it's hard to distinguish them from people. And it sort of gets into this whole, at what point, is an android a person? And there's this person who's actually a bounty hunter who goes around killing androids that have that have done certain things without spoiling too much. Let's say malfunctioned in a certain way. And along the way, he sort of starts to really care for these androids, and he realizes that they are starting to develop like human-like qualities. And it's a pretty cool book. I liked it. Thought it was pretty fun, and you guys should definitely check it out.
So this is the book that the Blade Runner movie was loosely based on.
That's right. If you've seen Blade Runner, supposedly neither Patrick nor I have seen Blade Runner.
I've seen parts of it. Like, I'm familiar enough. I think it's like the general, like that same theme, like a bounty hunter who like is trying to determine if these things he finds are androids or humans. Right.
Right.
This central theme and some other kind of sub themes is shared, but the actual story, I believe, is quite different. Gotcha, like you're not going to find the same scenes from the book or not in the movie and vice versa. That's kind of my understanding.
Yeah, it's pretty interesting. He administers a test to determine whether it's an android or a human, and the test by itself is kind of interesting.
I don't want to say anything because
we won't
spoil stuff.
Yeah, we're always worried about spoiling. We won't do that this time, but you guys should definitely check it out. I'm sure we've spoiled other things in the past. So what is your book of the show?
Mine is Foundation, book 1 of the Foundation series by Isaac Asimov. So actually, now I was trying to look. I don't remember how many books are in the series. There's a lot.
So yeah, there's 3, but then it's sort of like Star Wars. It's exactly like Star Wars.
Oh, okay. So it's a trilogy.
He wrote 4 through 6, and then he wrote 1 through 3 later. But you can actually skip 1 through 3 and still be okay.
I didn't know that's how it was. So I've read. I don't know how many books in this series. I think the trilogy, the first released trilogy or whatever, and then I've read various other books which are also in it, so I'm kind of confused now. And I generally know the story arc, but kind of not really. Gotcha. So it's confusing. But I haven't read them all, but I've read this book, and I believe I remember what happens. This is a very intriguing science fiction book where it kind of goes onto this idea of like which is classical in that it is actually true in history, that people tried to say, if you could measure kind of like all the variables of something, could you predict what was happening in the future? Right. So if you had like some isolated system and you knew the measurement of everything, is it deterministic, or is it still like, oh, you don't know what's going to happen because there's some source of kind of randomness?
Yep.
And so this is like a classic pursuit of philosophy, I guess. I don't know what exactly field it falls into. And so this kind of explores a notion of that, where like, if you could do this, what's called psychohistory, so like measurements about society, could you come up with statistical models that say whether or not certain actions are likely? And gotcha. So it's about this guy who is in the Galactic Empire, which is kind of like seen as this all good thing and has been ruling for like 12,000 years. And there's this guy who develops this psychohistory and begins to kind of understand that bad things are going to happen. And he's on a quest to try to stop it. And without spoiling anything, I mean, that happens like really early in the book, is you essentially figure out that he's like, maybe there isn't a way to stop it. So if there's not a way to stop it, is there a way to kind of like make it less worse?
Right.
And what steps would you do? And so he tries to make all these measurements and kind of take precautions to figure out what he would do. And that's what the book's about. But it's really interesting. I mean, it's been around a while, so some of these themes, I never noticed when I read books that are kind of older, like if the themes in them were original to them or reshared or common.
I was wondering
because like I read other books and I'm like, oh, I've seen this before, I'll predict the outcome of the book.
Yeah.
And it's because this was the original source of that idea, but it's been rehashed so many other times.
Yeah. There was a movie with, I think, Nicolas Cage, right, where either him or his daughter, somebody could know what was going to happen, and he went to a plane crash before it happened. And
is that a TV series or a movie? Yeah, I think I remember seeing this. Okay.
Yeah, he was.
I didn't see the movie, but I saw the previews.
Yeah. So this is a classic story, but this is.
But maybe he was the origin of it.
Yeah, this is the best incarnation of it. A lot of people have recommended this book.
Okay, yeah, Foundation by Isaac Asimov. It is good.
Isaac Asimov.
We're probably saying that wrong, but that's okay.
Yeah, poor guy.
All right, so on to our discussion.
Yeah.
Image processing.
Wait,
did you say this at the beginning in the lead-in? I don't remember now. Maybe not. Maybe this is a surprise.
I think I did.
Okay.
Anyways, so so we're talking about image processing, and it's pretty timely considering there's all this talk in Congress about drones and crazy. I
didn't make that connection.
Projects,
I guess, okay,
things like
interesting.
That. Oh, actually, I posted in the Programming Throwdown community that we're going to be doing image processing.
Oh, did you? Okay, good. Yeah. So people are doing their pre-work then.
Yeah. So people can ask us some questions, even though it's one way.
Okay. Wait, what? Okay, I don't know what that. All right, doesn't make sense. Okay, anyways. So to talk about what image processing is, like from a high level. So I actually struggled with this. I was thinking like, what's the best way to describe it? Because it kind of involves many related things in that they all start with an image, but you kind of from there it goes into like whole fields which are kind of under the banner of image processing. So Wikipedia, I just stole what they wrote because I thought it was pretty good. So they
did a really good job.
They divide it into 3 categories, which some of them I might name them different or maybe not, but it's as useful a categorization as any.
Yep.
So first is image processing, just image processing. So this is you start with an image and you get an image.
Yep. So for example, if you want to say blur an image, what you end up with is a blurred version of your original image, but you still end up with an image. It's just been transformed.
Right. Or you want to find even higher levels. Like I want an image that shows me where the edges in the original image are. So things that basically produce some sort of image on the output that's been processed in some way from it. And maybe it's just the same image. Maybe that's like
the ultimate process.
Okay. So the second one is image analysis.
Yep. So image analysis are where an image comes in and then some kind of measurements come out. So for example, maybe you're interested in what's called the edge density of the image. So what percentage of the pixels are edge pixels, right? So in this case, an image is coming in and just a number between 0 and 1 is coming out. You might be interested in other things like, for example, the saturation of the image. You might be interested in how much contrast there is. Maybe you want to increase the gain based on what the image looks like, and so.
Yeah, but it doesn't have to just be a single number though. Like I put into here things like a histogram.
Oh yeah.
So a histogram is like you go. So like let's talk about. This is a good point to talk about this. So different kinds of image. So you might think about immediately about like a color image, right? But a color image is really a case of black and white image, but you have 3 of them.
Yeah.
For a red, one black and white, essentially one grayscale image. Which I'm mixing up the terms. Okay, let's try. Okay, so let's start with this simple.
Let's do
a simple
image
case.
representation.
Yes, image representation. Okay, you go first.
You have binary images, which means a pixel is either black.
Wait, what's
or
a
white.
pixel? We gotta.
Okay.
So you have a grid.
Yeah, you have a grid of pixels. Each pixel represents some quantile of photons
or something, anything.
Yeah, it's true. Image really can be anything. But if you're talking about an image that you took with a camera or something like that,
which is a whole other discussion. But go ahead.
Each pixel is sort of a pool of photons over time.
It's a measurement. It's just a measurement.
Yeah. So, so you can have a binary image where each pixel is just a 1 or a 0. And that binary image could be a result of some threshold, some logic there, or who knows, right? You can also have a grayscale image, which means that each pixel is somewhere between completely white, which is usually represented as 1.0, or if you're looking at an 8-bit number, this would be 255, the biggest number, right? Or a completely black, 0, or somewhere in between. So that's a grayscale image. A color image is actually represented as 3 channels.
3 grayscale images.
Yeah, 3 grayscale. So one way of doing it is RGB. This is what your computer monitor, for example, does. So your LCD panel actually has a red, a green, and a blue light right next to each other. Or actually, this would be an LED panel. It would have a red, green, and blue light. They're very small right next to each other. And then by dialing each of those 3 in some combination, it can create any of the colors that you see on your LED TV. So you can actually, in image processing, you can take that apart and just look at the red channel, the green, or the blue channel. But it turns out that there actually are other ways to do this too. One way is you can look at HSL, which is hue, saturation, and light. And there's kind of trade-offs to doing these different techniques. But
well, wow, we can get on a lot of tangents here. So I mean, so RGB, red, green, blue is color. So because you can take red, green, and blue and represent any other color,
right,
with some combination. If you have infinite adjustments in each of the three, you can represent any other color. So those three work. But there are other color spaces which also work. But even ones which are colors like cyan, magenta, and yellow.
Oh, right.
These ones also are, colors that we see with our eyes. It's just another color, but they're, also a mix of them can create. And so like that's useful depending on what your end result is going to be. You may want to do that because it's better for printing. So printing is typically done not with red, green, and blue as lights are, but with cyan, magenta, and yellow, and sometimes black. But that's just kind of like a bonus thing, but cyan, magenta, and yellow. And so like that's just, you can transform from one to the other there. There's essentially a function which will map from one to the other for you. But then when Jason's talking about HSV, H, S, and V aren't colors.
Right.
So you kind of change your mind around. It's three numbers, but they're not colors.
But they can still represent all the same colors as RGB.
But with those three values, you can represent any color.
Right.
But they're not colors themselves.
That's right. So let's talk about them briefly. So hue is actually effectively what color you want to display. So whether it's red, green, yellow, blue, etc. That's the hue. The value is the amount of light coming in. So as you increase the value, the pixel gets more and more close to white. And if the value is 100%, the hue doesn't even matter. The pixel is just going to be white. And then saturation is the hardest one to explain. And basically, I even have a hard time just even visualizing it. But the important thing about saturation is that it's sort of one of these things that stays relatively constant. So even as the light passes over an object, the saturation usually stays pretty much the same. And so HSV is actually used a lot in image processing because it has some really nice properties. Like, for example, if you want to do edge detection, you can do it just on the V channel, right? Mm-hmm. And so that usually is pretty significant.
Or if you talk about, so we already kind of getting way off topic, but that's okay. So if you want to talk about like, you want to do photo processing, so like I took pictures of my kid and I wanted to change it, right? So if you just are only able to edit the red, green, or blue, we call them channels, just meaning one of those sets of numbers, all the red, all the green, or all the blue together, that is limited in what you can do, right? So a single adjustment in that channel, like multiply all the green values by 0.8. Right? There's limited, I can't necessarily do all of the adjustments I want.
Right.
Versus if I had also the ability to edit the saturation value, right? That may mean altering all of the red, green, blue values, right? But I'm only having to alter one channel in the HSV image, so transferring between them can be interesting. So before we got off, we were talking about making measurements. So we have this grid of numbers. Like let's just take a grayscale image, and you have a bin, and you want to say something about the image as an analysis. So you talked about like various measurements you want to take, but sometimes it's a series of measurements like histogram. So histogram is something not just images, but in general is used where you take a range and you make buckets.
Yep.
So if you had, in a simple example, if your grayscale was 0 to 255, you could have 256 buckets. And then you just go through the image, and every time you encounter a pixel, you take the value of that pixel and you increment the counter for that bucket by 1.
Right.
Starting at 0, and you count them all up. And then if you graph those numbers at the end, so for each bucket, or just write them out, each bucket, how many you have, it gives you an idea of where the content in your scene is. Like, it's really, really bright, then you're going to have a lot of numbers in 253, 254, 255. Mm-hmm. If it's really, really dark, you might have a lot of zeros and ones. And what you want to see there to best utilize the space of your image in some operations, you want to see that it's kind of level across the whole thing, because that means you're using all of the possible numbers to the best of your ability. Right.
Like so to Patrick's point, if you have, say, a camera, what your camera is constantly doing is it's taking a histogram of the image that it's seeing at the moment, and if the histogram is completely dominated on the right side, so if almost all the numbers are white, almost all the numbers are close to 1.0 or close to 255 and 8-bit, then your camera will actually lower the exposure. Is that right?
Well, it's a complicated because there's
Patrick knows a lot more about cameras.
It'll try to make the image darker. Let's just say that.
So the camera is constantly calculating the histogram, and then based on the results of that histogram, trying to allow less photons into the bucket next time around, or more, until the histogram falls somewhere in the middle. And so that's why when, let's say you have a camera or you're recording a video and you're in a dark room, and then all of a sudden you walk out your front porch, boom, like everything's super bright, and the camera all it sees is just this white flood. But then that histogram gets calculated and starts getting shifted over, and then it starts to see, oh, you're on the street or something like that. So
this brings up the reason for doing this, and this is something you run into over and over again in all the image processing, is that fundamentally you're trying to represent something which is, for most intensive purposes, infinite in scale. So like, there's, and you can have all the way from 0 photons, which is black, 1 photon, up to like, I don't even know, what does trillions of photons fall on a cell? Like, I don't know how many photons would fall. Like, there's this huge scale, right? Like, it could be any number in there. And yet the camera's forced to kind of pick somewhere in there to say, here's the darkest one I want to represent, and here's the brightest one I want to represent.
Right. And your eye does the same thing, too. I mean,
by shrinking your iris or making it bigger, right? Like, exactly. Your eyes dilate and contract, right? That is your eye trying to let less light in or more light in.
Yeah, so when it's a very dark room, your iris increases, and so this allows more photons to hit the part of your eye that's used for image processing. When it's very bright out, your pupils shrink, and then this causes less light to hit that spot, and so you're able to do sort of the same computation.
But it's fundamentally a limitation because we don't have eye sensors. We don't have sensors which can detect the whole scale. All the way down from 0 photons black all the way up to whatever, surface of the sun bright, right?
Yeah.
Like, we don't have something that can hold that much data all at once. And even if you did, you run into another problem, which is what I want to bring up here, is like, say you're representing 0 to 255. You only have 255 numbers to choose from. But yet, if you're inside a dim inside building, all of your numbers, if you try to represent, black hole black and surface of the sun white bright, if you try to represent all of those, all of your data might fall in just one number.
Right.
Because you have to adjust. And so a lot of the techniques you run into are people trying to do things to improve the fineness of the measurement. Because ultimately, once you take that measurement, that's it. You don't ever get more information. Unlike CSI, where you can just say, enhance, enhance, right? Once you take an image, that's it. Like, you only have that data. Now, you can do things to make it look better or to pull more information. But ultimately, that's, like, once you take the image or you form the image, that's it.
Yeah.
So if you only have 255 values, you only have 255 values. So you got to carefully choose what those map to.
Yeah, the CSI enhancing is hilarious. We watched a lot of those videos on YouTube. It's just ridiculous. I saw one where the person actually saw the killer off a reflection off the victim's eyeball. So they were able to enhance off this person's eyeball just 1 pixel and somehow create a whole another image. And it does not work that way. There's 2 limitations. One limitation is the one Patrick talked about, where in the end your values are distributed into these buckets. There's another limitation, which is that the pixel size,
resolution.
Right? Yeah, the resolution. So, photons are collected in these buckets, and the buckets are, dependent on your hardware. And then each bucket can represent 1 pixel, or there's some cleverness that they do there. But for the most part, there's no way to increase the resolution once you've taken a picture. Right. I mean, you can do some, you can increase the size of the image and then try to interpolate the pixels that aren't there. But you'll never be able to.
Yeah, but you're not creating new information.
Right.
We should probably talk sometime about cameras. This is actually really fascinating, right? But to try to avoid that topic, yes, resolution. You have one measurement of in space, and then one measurement in essentially brightness, color intensity, depending on what you're using. So the last one is image understanding.
Yeah, and so this is where an image comes in, and then what comes out is lion, prairie, or something like that, right? So you actually take the image and you convert it. You transform the model from a model of pixels to, say, a model of text, or maybe even a model in some other domain. So you can turn it from an image into
a thing,
some other thing. Yeah, exactly.
So interestingly, the way I think about this one is, and this maybe stuck with the way I took my courses at the university, but so I thought it's funny. So when you do image understanding or image recognition or a lot of image processing, what you're doing is ultimately you had the real world, and you somehow captured it through a drawing, a painting, a digital camera, a video camera, whatever it may be, some sensor. You captured something, right? So you captured an approximation of the real world, right? And then when you do image processing, image recognition, you're trying to get back to a model of the real world, right? And so you're trying to take that approximation and get back and infer stuff about what happens. So when you look at a pretty picture on your screen and you do, tweaking to it to try to make it look better, what you're trying to do is either make it look artistic or make it more like what your eye saw there in the real world. Or in image recognition, you're trying to get back, like, I want to model that, like, I know that those pixels were a cat. Okay, good, like, good cat. Then you can go a step further, and once you have some sort of representation, you can do 3D graphics, which is taking a model and trying to get back to making an image.
Right, yeah.
Which is kind of like, in my mind, that's like the pipeline. So you have, like, real world, some sort of sensor, and then you have image processing, trying to get to a model. And then 3D graphics is like taking the model and trying to get back to something that looks like what would have been taken with a sensor that would map back to the real world.
Yeah.
So
or thinking about it in terms of your brain, you have photons that are hitting your eye. You have image processing in your brain that's turning it into different. Your brain actually does many different filters, and so it turns into an edge detection, mask, and then several other filters, and then it hits your neocortex, which is responsible for saying, oh, this crackle of energy is actually a lion, right? And then you dream and you recreate the lion in your dream. So it's kind of amazing. Yeah. So those are the three big things. There's image processing, analysis, and understanding.
We're going to try to cover all of them at a high level.
Yeah, definitely.
Well, we already did, kind of, sort of.
Yeah. So images are really connected to matrices, which I think we did a show on MATLAB. If not, we definitely did. So go back and check out that show if you're not familiar with matrices and matrix operations, things like that. But in fact, a lot of image processing is done in MATLAB for this reason. So an image kind of fits naturally with a matrix because an image is just a 2D grid of values, and that's exactly what a matrix is.
Well, a grayscale one, or binary would be. But then a color would be
a 3D matrix.
X by Y by layer, number, channels,
Yeah. So, matrix math is really important for image processing.
So we talked a lot. We already started using things that may not be obvious with there. So we talked about like edge detection, or we talked about blurring. So these things which are kind of effects you do, or operations you do on an image. Some people might call them effects. It depends on what your domain space is. But so if you take these operations, so kind of like the base of that is the convolution.
Right.
So so matrix math itself, if you're talking about like linear algebra, is a lot more about like, inverse of a matrix and, matrix multiplying.
Finding the determinant,
these kind of things. And you do those sometimes on small pieces of an image or something, but for a lot of image processing, you're not talking about that same kind of matrix math. Right. Instead, you're talking about slightly different matrix math. And so one of those is, the basic one is like an image convolution. So this is, you have a big image, let's say a whopping 20 by 20 image, or 32 by 32. Let's take an old icon. 32 by 32 image, right? And you want to blur what's there. So you want to take what's there and kind of average it into the things around it.
Yep.
Right? So one thing is you could write like a little program that like, so for the first pixel, look at all the pixels around me and take an average of that, right? And then set that to the pixel I am. And then go to the next pixel and do the same thing. And you run into the problem like, you need two images, right? Because you need the image that's the input, because you don't want to keep blurring against something you've already blurred.
Right.
Or you might cause problems. So you're transforming from one image to another. So you're kind of updating this in place. But the way they represent that in image processing is an image convolution, where you take another matrix, so let's say a 3 by 3, and you put numbers in each of the cells, each of the cells of the matrix, and that represents what you want to, when you overlay that matrix in some portion of the original image matrix, you want to multiply that source pixel by this new value. So in the case of an average, if you had a 3 by 3, you'd want it to be 1 over 9.
Right.
So you want to take 1 over 9 times the pixel underneath me, and do that for all 9 pixels, add them all up together, and then set the pixel where I'm currently at to that value.
Yeah, exactly.
And then go to the next pixel and do the same thing.
Yep. So the big difference between matrix multiplication and image convolution is, with matrix multiplication, if you remember if you have say an X by Y matrix, you have to multiply it with another matrix that's a Y by Z matrix. So in other words, the number of columns in the matrix that you did on the left side of the operation has to be equal to the number of rows of the matrix on the right side. And you end up with what's called, this is known as the outer product of the two matrices, right? So in image convolution, it's totally different, where you are basically, you're taking a 3x3 window of the original matrix, and then you're doing the outer product, or the inner product rather, of that and this convolution, what you call a convolution mask. This is what Patrick is talking about, the 1/9. So you take a small piece of the image and you do an inner product between that and your mask, and then you take that result and you put it back in where the center of that window was that you took out. And so you do that for all the possible windows you can cut into that image. And what you're left with is a new image with all new values.
So you can get more advanced. So this 3x3, 1/9 averaging thing, right, will produce something that looks a little bit like a blur. But it might not be pleasing because, for instance, let's say it was bigger, a pixel that's far away is going to contribute exactly the same as a pixel that's really close to the center.
Right.
And that's a problem, because that's not how blurs in physics really work. So, and if you want to try to model what would be in the physical world, a blur, like looking through something that's blurry, you're going to end up with more what's called a Gaussian blur. Yeah. So then there's something to tell you what numbers to stick in each one of the mask cells, so that pixels far away contribute very little and pixels very close contribute a lot. Right. And this produces, a more pleasing blur. And so you'll see even in Photoshop, there's, Gaussian blur this image, and it asks you questions. What size of Gaussian blur do you want? What standard deviation of Gaussian blur do you want? Right? And all this affects how much the nearness or farness of pixels contribute to what the value of the destination pixel should be.
Yep. Yeah, there's a lot going on in image processing. It's a lot of heavy math, but it's also a lot of fun.
It is. So, cool the nice thing is you do something, with many of these, you do something and you get back some picture you can look at, right? Yeah. Or you get some answer out that's probably wrong, cat and you want a dog or something. Yeah. But you get something back, and especially the ones where you get an image out is really rewarding, because you can tweak something and see what happened, right? Yeah. And
And so we'll do a little bit of a tangent. We're actually going to do a 2-part series on AI in the future, but for this episode, there's also a lot of AI in image processing, and we'll kind of gloss over that because we'll cover a lot of it in a future episode. But needless to say, you have to do a lot of AI. If you want to detect whether this image is a cat or a dog or neither, that's fundamentally a artificial intelligence or a machine learning problem. So often the way these techniques work is they convert the image into what's called a feature vector. So imagine all those things that we talked about earlier, like the edge density, histograms, a histogram of the edge. You can actually do an edge convolution, and now you're left with an image where it's white where there's an edge and black where there isn't an edge. And it's gray where it's not really sure if there's an edge or not. You could take that image and then create histograms of that image. Is that image really bright? Is the histogram far to the right? If it is, then there's a lot of edges in this image. But it's better than having that histogram is more information than just having one number, right? As to the edge density. So you can take these edge density, these scalar values, you can take these histograms, do some convolutions, some more histograms, and you end up with just a ton of numbers, but each one sort of has more meaning than a single pixel in an image. So a single pixel really doesn't tell a good story, but a lot of these features in the feature vector kind of tell a story about the image. So many AI techniques will first do a lot of image processing and image analysis to create a feature vector, and then at that point it just becomes a standard AI or machine learning problem. At that point it doesn't even matter that you're using images, because you've converted the image to some other representation. So we'll get to more of that later, but that's why a lot of this image processing is so important, is that it sets the groundwork for doing some of that other cool
I guess
stuff.
That's good. The first two things we talked about, image processing, image analysis, are really separate and linked together, and then they produce something which then is further processed by some, like you said, general machine learning algorithm.
Mm-hmm.
And it's the fact that it came from a source that was an image that matters, that makes it image understanding, makes it image recognition.
One other part of image processing that's really important is, a lot of people say, well, image processing, that's just AI, right? But the reality is, your eye, so just from a physiological standpoint, your eye and the early parts of what's called your retinotopic map, the part of your brain that takes a signal from your eye and just does some basic things to it, that's kind of just the way it is because of biology. And so a lot of image processing is just about sort of capturing the way that biology made us how we are. And so, for example, one common thing in image compression, which image compression is a way to represent an image using very little data. By default,
less data.
Yeah, by default, an image is, as we mentioned, a set of pixels, and you could just store a number, or I guess 3 numbers if it's color, for every pixel. But this is a lot of number stuff to store. So image compression involves sort of storing coefficients of a function. So you might have some function that's very good at describing almost any image, as long as you set a couple of parameters right. And so image compression is about finding those cool functions and then at that point just using those coefficients for the function to represent the image. So one trick to image compression is the fact that our eyes aren't very good at representing blue. So it turns out that light blue versus dark blue, our eyes just aren't good at distinguishing the two. If I gave you 2 shades of blue and they were very similar, you would have a hard time knowing that they were different. But red, on the other hand, we're actually very tuned for red.
Green.
Both. Red and green. Yeah. So they, I think it has to do with like predators or, people hide. Actually, Patrick is right. Green is the one we're most tuned to. And it has to do with, predators are in the jungle and we've been biologically, evolved to be able to pick things out from a jungle, pick the lion out that's chasing after us. Like the ones that saw the lion in the jungle survived, and the ones that didn't, those early humans died. And so what's left are people who are very tuned for green and red. So, image processing, part of image compression is taking advantage of the way that our eyes and the way that our brains work. And so once you've captured a lot of that, then you can do AI, machine learning, cool stuff on top of it.
I think there is an interesting point there that a lot of image processing is knowing what your ultimate goal is. Mm-hmm. So a lot of this it's a field that's very ripe with applications because I'm sure there's theoretical stuff that goes on, but a lot of it you kind of relate back to something somebody's trying to do. So like you're saying compression based on the human eye. Well, it depends on what you want to do with it, right? If you're trying to make certain kinds of measurements, you might not want that. You might want, representing what a camera would see really, really well. Right. Because that's what you're intending to do. You're going to use a camera to navigate a robot, right? And then so you want the thing that measures best the scene you're in versus acting most like a human. Yeah, exactly. Just because humans aren't good at representing blue doesn't mean that robot drones should have the same handicap. Right. So, but it's interesting because you kind of got to know you want to do something better, but you need to have your end goal in mind to figure out what's the best way of doing that. Yep. Or any of these things. So, even blurring. So you might want to blur an image, again, to help on compression because you want to say I want to represent with less. So I'm going to kind of do a little bit of a blur so that when I subsample the image, when I take only every other pixel, I know that I am not going to just completely lose what was in between. I get some of that data. But you might want to do a different blur for that than a blur that's just, to make somebody's face look less blemished in a photograph. Right. When I'm going to send the picture to my mom, I want to apply this blur because it kind of makes the wrinkles look a little bit less noticed because they kind of blend in with the rest of the skin, right? Yep. And so that blur may be a very, very different blur than what you're trying to do when you're trying to do compression. Yeah, definitely. Yeah, so a big part of image processing is sort of deconstructing how our image system works. Many of the applications are sort of to either mimic a human or to augment a human's vision or to provide some information. Those are my favorite, augmenting humans. Augmenting a human in themselves. So there are a lot of common challenges across this, though. The first is that, everybody knows the whole megapixel race of cameras and just in general sensors and the data. But it's not just about how many pixels you are, but about the bit depth is what it's called of the pixels. So instead of using 256 values for every color, I want to use 1024 for every color, or I want to use whatever some outrageously large amount of data to represent blue. So I want like a 16-bit image where every channel is 16 bits instead of just 8 bits. So I can represent that many more levels in my image. And then if that source data is better, all my further processing is going to be better. But every time you do this, you make the amount of, if you're going to do, for instance, convolution, the number of times you have to do convolution and the precision with which you have to do it just, gets bigger and bigger. And you run into kind of a squared problem, right? So like if you increase each of the dimensions by 2, you've really made the size of the image go up by 4. So, this is like one of the fundamental issues with image processing is that you end up, as your images get bigger and bigger, you have tons more processing that you have to do. And in a lot of applications, like in robots, where a lot of image processing is done, you have a deadline. You can't just sit around chugging for 5 minutes saying, please wait, please wait, please. I mean, you have to get some answer about what is the robot saying, what does the robot need to do. And so you need to be able to do these very large calculations very, very, very quickly.
Yeah, definitely. Yeah, I mean, I think the amount of data is really staggering. I think that a lot of people, it's kind of hard to appreciate it. But I mean, one way to look at it is, I was trying to look this up on the internet, but it's not easy to find out. But one thing I did find on the internet, there's about 100,000 words in the Oxford Dictionary. So there's 100,000 words that need to be defined, right? So let's say each definition was, how many words would there be in
10.
10 words in a definition? Okay. So there's 1 million words in the Oxford Dictionary. Like if you were to count how many words in the dictionary. Let's say the average word is 3 letters long. That's 3 million letters in the whole dictionary. So that is only, what is the square root of 3 million? It's like, I don't know, 5,000 or something. The point I'm getting at is, yeah, it's about 5,000, maybe 5,500. So if you have an image that's 5,000 by 5,000 pixels, let's just say it's a grayscale image, in that image is enough data to hold the dictionary and all of its definitions, right? The entire dictionary. And people take pictures with 5,000 by 5,000 pixels. Nowadays, cameras can do that, modern cameras.
So that's not that big. Right?
Yeah.
You said it was 3 million, right? So that's 3 million, that's 3 megapixels.
That's 3 megapixels. So every time you take a 3 megapixel picture, you have enough information there to represent the entire Oxford Dictionary.
Well, way more, because you're taking it in color and you're taking it with
3 times as
higher
much
bit depth than that.
Yeah, so think about the scale of the amount of data that you're processing that has to be processed. It's massive. Right?
So it is really crazy because sometimes you go look at an old text file, like, wow, that was a really big, I typed a lot of words in this doc file or this PDF or whatever, latex.
Yeah.
If you're, I typed a lot of words here, and then you go look at the size and it's like, what? It's so tiny, right?
16,
and one image, will easily be, 20, 30 megabytes, 40 megabytes, and that's with compression sometimes,
Yeah.
And it's like, wow, this is crazy. And then if you talk about video, so we talked about this. So image processing plays a lot with video, but all video is, so aside from the compression parts of it, video is just, some regular interval of pictures.
Right.
So you just have a camera that's taking pictures at some regular interval. So in case of broadcast TV video, it's 30 frames per second, or 29.997
yeah,
or whatever.
29.9.
But you have 30 times a second the camera is snapping a picture, snap a picture, snap a picture, snap a picture.
Yeah.
30 times every second. You have 30 of these, and if you're going to process it in real time, quote unquote, that means to keep up, you need to process it in 1/30th of a second.
Right.
Which is really fast.
Yeah.
These images can be really big.
Yeah, imagine you're a production movie. They're filming a production movie, right? So that's easily going to be 3 megapixels because it's going to go on a huge TV screen. It's probably going to be much more than 3 megapixels.
Yeah, I think HD TV is about 1080p is about 2 megapixels.
Yeah, but what would it be for a
1920 by
theater?
1080.
I mean, this would be
so
a
4K.
Theater.
So it's 4K by
I don't know. It's huge.
Let's call it 10 megapixels.
10 megapixels. So, and you're recording 10. You're taking a 10 megapixel. You're taking 30 10 megapixel pictures every second.
Well, movies are 24 frames per second.
Oh yeah, that's true. Okay, 24. So you're capturing
old ones. New ones are different.
Are they really?
Yeah. Well, this is the whole Hobbit thing. You didn't hear about. Okay. Anyways, let's skip this because this is a tangent.
So you're taking 24 pictures, each picture holding more than the entire dictionary worth of data every second. So it's staggering amount of data, and only now actually that where we have the kind of computational power and the knowledge of distributed systems, things like that, are we able to sort of tackle videos and do the cool kind of things that we have been wanting to do. So.
Yeah, and still it's hard. Like if you've ever done video processing on your computer.
Oh yeah, on one machine.
So like at first you're like, oh man, like I'm using this to edit this video and I'm trying to do trimming it or whatever, doing various things. You're like, why does it take so long? And then you export it. It's like, oh man, it's gonna take an hour. Like what? It's a 5-minute video, and you get kind of mad. But then you think about like Jason's trying to get us to get a little bit of an understanding of how much data it's really got to go through, and you begin to kind of realize why it's taking that long, even on really fast modern hardware.
Yeah, definitely. So some other challenges of image processing besides handling all that data is that you are looking at an image, and depending, there are the cases where you have video, but in many cases you're just looking at a single image. And so you might be at a frame where there's a lot of, say, what's called occlusion. So for example, you might be trying to build a person recognizer, a person detector. Like, yes, if there's a person in this image, no, if there isn't. And your system does really well when it's head on. So if it's taking, if you're taking a picture of your brother and he's just like smiling, standing next to a rock or something, it does a great job. What happens, all of a sudden your brother turns to his side, and then now, you can't tell, his arm is just on top of his shoulder in the picture, right? And his other arm is completely occluded, which means the picture, because it's two-dimensional, it's sort of squished his arm behind his body, and you can't even tell it's there. So occlusion in image processing is a massive problem. I mean, if your image processing algorithm detected humans by, say, looking for two eyes, now, if the person turns to the side, one of their eyes is occluded. Now your image processing algorithm doesn't work anymore, right? So occlusion, and along the same lines, orientation. So, even if something isn't occluded, you might look for two eyes and you might look for them to be around the same size. But if a person turns their head to the side 45 degrees, now one eye is bigger than the other, right? And so your algorithm doesn't work. So,
well, one eye appears bigger than the other.
Oh, that's right. Yeah. No, actually, it grows. As you turn your head
creepy.
to the side, your eye just bulges out. So these are huge problems to deal with.
Well, even if you manage to capture the ideal, shot of the person, you still deal with a lot of noise. So this is something else. Like,
oh yeah, noise is also.
I have an eye, and I have this perfect measurement of Jason. The color of his eyes, the whatever beautiful. What color are they?
Creeping me out.
Okay. So you have a perfect representation of his eye, and you're using ultimately something to take a measurement of the scene,
right,
to be able to do this. And we talked about first of all, there's a problem of bit depth. Like I only have 256 levels to choose from, and I have to represent everything in the scene. So challenge 1. Challenge 2 is, photons are falling in my sensor, and I need to be able to measure them perfectly, exactly.
Right.
Well, that just doesn't happen.
Yep.
So even if you had a perfect number to represent it, you have to perfectly make that measurement, which would never happen. So if you had think of you're looking at a whiteboard, a dry erase board, and you took a picture of a pure white erase board with perfect uniform lighting, none of this would happen, but it's all perfect, right? And you try to take a picture of it, you're still not going to get all white. You're going to get some stuff that's slightly less white than other stuff, and it's going to have all these little variations in it just from the fact that you can't capture a perfect image of it, or there might even be what if there's a little dust in the air, scattering
that's exactly
it, or heat waves coming up from the ground, right?
Even if you could exactly measure exactly how many photons hit this spot, the reality is it would be different because one photon bounces off a dust particle in the air, and two other photons collide and bounce off in a weird way, and so there's always going to be a lot of noise no matter what.
And then that doesn't even get into the aspect of when you're taking a picture, it's not instantaneous. You have to sit there and look at it for a little bit. So this is we talked about shutter time, shutter speed. So even if there's not an actual shutter, there might be an electronic shutter, but it's something to say how long to let the photons collect for.
Right.
And that length of time, the thing can move. Jason can blink. Now his eyes are half open, half closed in my image. What the heck? Now this is a problem for me, right? And you have to deal with that.
Yeah.
And all of these image processing things.
Yeah, and I mean, and the other problem too, and I think we should talk about, is that all of these effects are cumulative. If you have some algorithm that does edge detection, let's say, it's not going to be perfect. There's going to be some edge cases, things like that, and it's going to sort of introduce noise, and you're going to lose some of your information, right? And anything that runs on top of that is already at a disadvantage, and then it's also going to introduce its own artifacts, right? And so all these artifacts are cumulative. And that's one of the biggest challenges in image processing is knowing where in your pipeline you can get the most bang for your buck.
Yep. All right. Well, we could go on for a long time about this.
Yeah,
but
we've done this for a long time.
Talk about some tools.
Yeah.
So first one that I'll talk about is OpenCV, which is Open Computer Vision.
Yeah, it's an amazing library.
There's a lot of history to this. I think it used to be an Intel product, and then it was open source, and now, anyways, getting aside from the background of it.
There's a lot of not plugins, but wrappers, I think is what the right term. But you can write OpenCV. You can access OpenCV code from Java, Python, many of them.
Yeah, so a lot of them, because it's basically a framework. So to represent images, we talked about like, they're matrices. But there's a lot of common things you want to do, like, I want to represent a convolution kernel. I want to represent an image. I want to like all these different things. There's a common kind of way to do it. So part of what OpenCV is doing is like, here's a common framework for doing that.
Yep.
But then, like Jason said, a lot of not only languages work with it, but a lot of people have written their university research paper in OpenCV. So they'll release like, here's my OpenCV code that does this crazy, fancy whatever magic that you want it to do. Or like, here's an edge detector. Or even they have things like, here's something that if you take two images, it'll try to align them so that they, kind of overlap correctly because you had slight vibration in the camera between the two pictures.
Yep.
So things as complicated as that.
That's called image registration. Yeah, when you have two images and you think that they're the same content, but one is maybe shifted or skewed or rotated, and you want to sort of come up with the transformation that aligns the two images. Yeah.
Right. So, they all even have code as complicated for things like that. I don't think they go as far as like having optical character recognition, OCR, or like detecting cats. But the basis for that, is kind of in there.
So they have several methods for transforming an image into a set of features, which is what we just learned this term, which is image analysis. They actually have several libraries that do that. So they have SIFT, which is Scale Invariant Feature Transform. They also have SURF, which is similar to SIFT, is not as good, but it's high performance. I forgot the acronym stands for, but basically it does the same thing but faster. So it's really meant for videos and processing just many frames of images. And so if you need, to just get an image and just turn it into a bunch of features for you to do something else with, OpenCV has all of that built in.
Yeah. So there's also the Python imaging library.
Yeah. So. This one's is in Python. It has a lot of sort of convolutions, these kind of things. It works with NumPy. So if you are a Python user and you've needed matrices before, I'm sure you've used NumPy. This is tightly integrated with that. And it supports opening and saving files in many different formats. So
we already talked about MATLAB, Matrix Laboratory, but MATLAB, or I guess Octave has probably
Octave has
image processing in as well.
Yep.
So one of the nice things about MATLAB Octave in the image processing is like there's a lot of code to write. If you're using a language which you don't have a good library for already, just to like get to this array representation, and the code is what it'll be, not a matrix but an array. And so you have this array representation. Once you get there, there's a lot of fun you can do just to play around. But to get there, there's a lot of code. So having a batteries included something that does that, or finding a good library to do it for you, is a huge thing, because you don't want to figure out how to, it's not stored as just a list of numbers. There's like headers, and there might be various compression, and you got to figure out how to undo all of this stuff to get back to your array of numbers. And things like Python imaging library, MATLAB, OpenCV, these have those functions in them, which is really good because that stuff's interesting, but for me, that's not the part I wanted to play with when I started.
Yeah, exactly. I mean, the other thing to know is if you aren't taking the video yourself, so in other words, if you're recording a video on your camera, you can record the video even uncompressed, right? But you could also do, MPEG 2 or MPEG 3, and you just know what it is. But if you want to just collect a bunch of videos from the internet, they could be encoded, and each one could be encoded slightly differently. Like one could be MPEG 4, one could be XVID, one could be uncompressed, and you don't want your image processing algorithm to be dependent on one of these input formats. So by using something like PIL or OpenCV or MATLAB, you just say, hey, take this image and turn it into a bunch of ones and zeros. Like it's JPEG, it's PNG, it's MP4. I don't know what any of those mean, but I just want, a matrix, and it will handle all that stuff.
So the other thing, and it's kind of a tool, kind of whatever. Anyways, for photographers and images are taken with cameras, especially, you have Photoshop and GIMP.
Yep.
And so this is still useful because, like I said, there's things like Gaussian blur in there. You'll see that, or you can do things like do edge detection. It'll show you what the edges in the image are, which are transitions from dark to light or light to dark, or colors, but they'll have those kinds of things in there. So they're useful for like, oh, that's what that looks like really quickly. I wonder if that's what I want to implement or not. But even otherwise, sometimes if you want to pre-process your image in some way, so like, oh, I got this really dark image, and I'd rather make it brighter because my algorithm works better that way. Sure, you probably should write something that does it automatically in your code, but initially you're not going to have that. So having something like GIMP or Photoshop, whenever I was doing image processing, I use these tools very heavily.
Yep,
both for opening images and then like, oh, I want to crop it down to a power of 2 size because some algorithms want that. Like doing all those things, I don't want to write code to do that because it's typically a one-off where I need to use human judgment to make something. And sure, a final system can't do that, but for testing and prototyping, these tools are invaluable.
Yeah, definitely. They're both awesome. Highly recommended.
And then also, I guess if you get to become an image processing guru, you can contribute to GIMP or go work for Adobe and make the next Photoshop because they really have to do crazy stuff in there to implement all these things we talk about.
Yeah. I mean, there's the latest Photoshop has this ridiculous stuff. Have you seen this magic eraser?
No.
Well, it uses a bunch of techniques, really advanced techniques, but the idea is you can sort of erase something and it will blend in. It will replace it with, blended in of its surroundings.
I've seen this before. Yeah, content-aware.
Yeah,
stuff,
that's what it is. It's
so
the
like,
same thing.
yeah, like I'm deleting something from grass, so it knows to go find other grass and like stick it there from the image.
Yeah, and it sort of keeps the frequencies intact, and it keeps like L2 continuity, so it actually you can't even tell that there was the pixels next to.
Right, so there's a huge math research definition of it, but then ultimately those people aren't using it. It's people who are like photographers saying like, oh man, there's like an ugly cockroach on this wall in this house, and I want to just like remove that cockroach. Like he doesn't want to think about, I wonder what the gradient in this area needs to be for. Okay, gradient is actually an overloaded term there. That's multiple meanings. So okay, anyways, we'll skip on.
But yeah, it's pretty amazing. Photoshop and GIMP's a great way to start off. But hopefully you'll make some of your own image processing algorithms and share it with us. It'd be pretty cool.
Yeah, it's a huge field. This is only a light glossing over, but hopefully we've enlightened someone or
definitely. If you have
at
any
least entertained you for an hour.
If you have any questions about image processing, feel free to post it on the discussion on the Programming Throwdown community. So.
All right, well, that's all I got.
Cool. Have a good one, guys. See you next 2 weeks.
The intro music is AXO by Binar Pilot. Programming Throwdown is distributed under a Creative Commons Attribution Share-alike 2.0 license. You're free to share, copy, distribute, transmit the work, to remix, adapt the work, but you must provide attribution to Patrick and I, and share alike in kind.